Start recording. Excellent. Today we're going to talk about Taylor series and Taylor polynomials. Let's write that out. Okay. Let's zoom in some so this is a little bigger. Taylor series slash polynomials. Okay. And if you remember, we built a couple out of like e to the x. If you went in sine x or cosine x. But the basic gist is this. I'm just going to give you the formula. We'll talk about why this works and what's going on here for real. Okay. But what it really is, let me type this. It'll be so much nicer. I'm so smart. Okay. A Taylor series polynomial. So let's say a Taylor polynomial, I guess. Polynomial. There you go. It's a polynomial function that approximates another function. Okay. It is exactly equal to the original function at the center. We're going to call it x equals c, and all order of derivatives are equal to the original function. Derivatives at x equals c at the center. And that's basically what we're going to do. We're going to build a function, a polynomial, that matches the derivatives of another function, and it forces it to conform to this other function. This is what's going to happen. Okay, so the basic formula for it is this. The basic formula, we'll take a look at a couple examples. Okay. So if it's a series, the difference between the series and a polynomial is the polynomial stops somewhere. It's similar to like the fourth partial sum versus the actual entire series. Okay, so a Taylor series centered at C centered at x equals c is this, the summation from 0 to infinity of the nth derivative at c divided by n factorial times x minus c to the nth power. That seems kind of scary looking. Okay. So, I'm going to write the first few terms of this so you can see what it looks like. So what this is equal to is, and even though there's x and c, c is some number that you don't guess, like c is going to be given to you, okay? X is going to be left in it. Just like, remember we found tangent lines and we had x's in our answer, and you could plug an x value into the tangent line and it would approximate the function we started with. That's exactly what this is, just way more in depth, much better approximations. Okay, it's an extension of that idea. But if you drop a 0 in here for n, n's again called the index, you get f to the 0 of c, okay? That means the 0 derivative, which is just the function, okay? So the very first term of every Taylor series is just the y value at the center, okay? Technically, that's divided by, you think about it like this, 0 factorial times x minus c to the 0. But all that boils all the way down to just f of c. That's the first term, okay? The second term, when n is 1, is the first derivative at c divided by 1 factorial, which is just 1, times x minus c to the first. Okay? The next term, when n is 2, is the second derivative at c, you see the pattern here, times 2, divided by 2 factorial, times x minus the center squared. Okay? And for fun, Lily, what's the next term? What could it be?
F triple prime of
So
c
good.
over 3 factorial times x minus c to the third.
You're so good at this. You have an excellent teacher. And after the third derivative, they usually just start putting like a number up there. So they write like f4c over 4 factorial. So plus dot, dot, dot. And that goes on forever because we're adding it up to infinity, okay? And the idea is if you do that out forever and you plug in an x value, if the series converges, it converges to the value of the function at that point. Okay? The reason why it's an approximation is because you can't go out forever. You got to stop somewhere. Okay? So that's Taylor series centered at C. We're going to build one in a second. Taylor polynomials are just this stopped somewhere. So if they said find the fourth degree Taylor polynomial, it would be all the way out to that fourth term and then stop. There would be a dot, dot, dot. It would just be the fourth thing. Sound good? Okay, keep in mind, the power on x will always match the derivative you are on. Okay? Because we're going to get a discrepancy here when we start looking at some of these between what n is and what power we're on. Okay? So it doesn't matter what you plugged in for n. It matters what the degree is. That tells you what term you really are. All right, so let's build one. Oh, by the way, this is just a little tidbit. If the center happens to be at 0, then it's called a Maclaurin polynomial or series. So if you see, find a Maclaurin polynomial, that means centered at 0. If they say Taylor polynomial, they got to tell you what the center is. Again, you're not going to find the center. They're going to tell you what it is, and you build it. Cool. So our first question that we are going to look at is number 1. Find a, what do you want to do? Fourth degree? Fourth degree sounds good. Fourth degree Taylor polynomial. Well, let's say Maclaurin. We're just going to do it at 0. For f of x equals ln of x plus 1. Okay? So fourth degree means we need to find all the way out to the fourth derivative. But let's be very careful here. You know how when we find the slope of the tangent line, we find the derivative? We don't plug that into the slope. We plug whatever x value we found it at, right? The slope is a number. The same thing is true here for these derivatives. Okay? The derivative will not be a function. It's going to be a number. So you find the derivatives and you plug in the center. That's it. So we're going to find the derivatives and we have to plug in 0. So what we need to build this, the only thing that changes a Maclaurin or a Taylor polynomial from one function to the next is the derivatives. They all have the same factorials. They all have the same x minus c to the power. It's the derivatives that change it. Okay, it's like the DNA of the whole thing. So we need to know what's f of 0. We need to know what's f prime at 0. We need to know f double prime of 0. Let's close this off here. Getting sloppy. F triple prime at 0. And the fourth derivative at 0. Okay? What's f of 0? ln of 1, which happens to be 0. Everybody knows that's 0. 0. Okay? F prime of 0, the derivative of ln of x plus 1 is 1 over x plus 1. Okay, so that's 1 over 0 plus 1, which is 1. Okay, I don't know if you guys can do this in your head. I'm just deriving this thing. So the next derivative is negative 1 over x plus 1 squared. At 0, that equals negative 1. Okay? The next derivative is 2 over x plus 1 cubed. That's going to be 2. Cool. And the fourth derivative is negative 6 over x plus 1 to the fourth. And that's negative 6. Everybody good? Pretty straightforward. And now we're just going to drop it right into our little Taylor series formula, okay? So, they label this P sub 4 usually. It just means the fourth degree polynomial. Okay? Our first term is just the function value at the center, which at this particular instance is 0. You don't have to write that, but it is 0. Cool. Plus the first derivative divided by 1 factorial times x minus the center, which is just x. Okay, we can write this all the way out, I guess. Like, you can simplify this down a lot, but that's what that looks like, okay? Plus the second derivative divided by 2 factorial times x minus the center squared. It was fun. Yeah, it's fun. Thank you. Good. That was the correct response there. 2 divided by 3 factorial times x minus 0 cubed. And then minus 6 divided by 4 factorial x minus 0 to the 4th. There you go. Let's get that all on one screen there. And we're going to reduce that all the way down to what it really is, which is x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4th. So it actually works out relatively simple. And that's kind of like weird about these. Like they end up being semi-simple. There's patterns to them, but they represent or they model these like complex functions. Yeah, everybody with me so far? You're feeling good? You got a 4-degree Taylor polynomial. Okay, if that's what it says, you just do that. Find the first 4 derivatives, plug them in. Okay, on the AP test, this might be like a multiple choice question. Okay, so that's question 1. Question 2 would be like to use this to approximate. So let's say we want to approximate ln of 1.2 with your polynomial we just found. Just like with a tangent line, if you want to approximate it at a certain x value, just plug it in for x and see what y is. Cool. So be careful here. It looks like we should plug in 1.2. It's not what we're going to plug in. What x value do I need to plug in to get ln? Remember what function we're modeling. What's x got to be for that to be ln of 1.2? 0.2. So we're going to plug 0.2 into our polynomial, which is weird. Okay? So ln of 1.2 is approximately equal to a piece of 4 of 0.2, which is 0.2, which is 2/10, minus 1/2 times 0.2 squared, which is 4/100ths, plus 1/3 times 0.2 cubed. What is that? 8/1000ths. These reduce down. I should have made that a 1/5. Minus 1/4, 16/10,000. Everybody okay with that? This is probably a little bit overkill doing this by hand. If we had a calculator, we could just do it on a calculator. What's our common denominator? Let's just do that on a calculator. I don't feel like doing all that workout. Cool. So it's 0.2. And I'll show you that this is going to end up being close. Minus 0.5 times 0.2 squared plus 1/3 times 0.2 cubed minus 1/4 times 0.2 to the 4th power. And if you do that, you get this. And if you tell me what ln of 1.2 is, it should be close to that, unless I made everything up. There you go. Pretty close. Okay. Now, you're probably thinking, what's the point of doing that? You just plugged in ln of 1.2 and got an answer. Like, why? They use this in like programming a little bit. Like I told you, they use like Taylor series stuff like this to like kind of compress things like pictures and MP3 like audio like series are used in there. So, by the way, you guys get the basic gist of this. Ask to find a polynomial. Your homework is that, by the way. It's page 630, number 7 through 9. That's it. Okay. Except your homework's a little tricky. You're gonna love this. It's not to find the Taylor polynomial. It's to find the Taylor series, which we haven't done yet. That's my next question we're going to answer. Okay, so number 3. Come on now. So what this is asking for is this. It doesn't want like the first 4 terms. It wants us to generalize it and put it into sigma notation with the summation. All right. So it wants to know what series is going to give me basically any term that I want to find. Okay. Now, hopefully you see that there is a pattern to our polynomial up here, right? What's it look like this should be? Notice. Any takers? Oh, Adrian. What? 1 over n what? Okay, that's going to work out. Definitely over n. Definitely an x to the n. It's got to alternate. So what do we got to put in there? Okay, so let's check this out. And where should n start? So yeah, you always think about the degree of your first term. The degree of our first term was 1, so let's make sure that matches up. Since the exponent there is n, we need n to start at 1 and go to infinity, and this is slightly off. Why is it slightly off? What do you get when you plug 1 in there? You get negative x. We need positive x. So how do we change? What do we do to our exponent? N plus 1. Okay? That's the Taylor series for ln of x plus 1. But you see, so it's a little harder to find the Taylor series than it is the polynomial because you got to find that, like, the pattern in the terms. Okay? Let me say this too. The fact that, and this is true of any polynomial that's like this, the fact that I start by plugging in 1, like the very first term of this is x. The very first term of a Taylor polynomial should be the value of the function we're approximating at the center. If you don't see it there, if our first term is x, that means the constant must have been 0, and that's why we're not seeing it. Okay? Some polynomials are going to start out on x cubed. If that happens, that means the constant, the first derivative, and the second derivative were all 0, and that's why you're not seeing them. Okay? Cool. Another way to think about this too, like the Taylor series for any polynomial, we already wrote this out here. Well, Maclaurin, I guess, would be at 0, right? So we'd have this. This is the Maclaurin polynomial for any function. If you can find the pattern in the derivatives, then you can just drop it right in there, and that'll tell you what the series is. Do you guys notice the derivatives of ln of x? What are they? 1, -1, 2, -6. The next one's going to be 24. The next one after that's 120. What are those numbers? They're what? Where are those numbers coming from? This we got as 1. This we got as 1. This was 2 times 1. This was 2 times 1 times 3. This was 4. It's the factorials. It's not triangle. It's the factorials. Okay? These are factorials, but it turns out, look at this, the third derivative is 2 factorial. The fourth derivative was 3 factorial. So whatever derivative we're on, whatever n is, the factorial that's on top is really 1 less than that. So our derivatives are really, in this particular case, n minus 1 factorial starting at 1 and also alternating. So we still need that -1. But what's n minus 1 factorial over n factorial reduced to? 1 over n, which is why these two are the same exact thing. Cool. One is you just write out the whole series and see the pattern, and the other you can just find the pattern in the derivatives and drop it in there. Feeling good? So again, your homework is to do those 3 questions. We're going to look at an AP question today too. It's going to blow your minds. But before we do that, you are going to memorize some Taylor series. One of them is ln of x plus 1. You know how you know the derivative of sine of x is cosine of x? You're just going to know these. Okay? So let's get this out of here. Like you want the simplified versions. So that's one of them. Here are the other ones that you are going to know. Let's zoom in. Let's write these big. So you're going to know e to the x is the summation from 0 to infinity of x to the n over n factorial. These are the Maclaurin polynomials or series, okay? You're going to know sine of x is the summation from 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. You're going to know cosine of x is the summation from 0 to infinity, -1 to the n, x to the 2n over 2n factorial. And by know these, I mean like tomorrow when you come in, you should know these. It'd be good. It'd be good if you were to know these by tomorrow. Just saying. I'm just saying you should know these by tomorrow when you come in the door. It'll be good for your heart if you know these. It'll be good for your grades to know these. Yeah, definitely know these. Cool. That's what we just did for ln. So we built that one, right? We saw where that came from. We can build these other ones. Like they work. We can find the derivatives and see what's going on. Okay. And then the last one, we already know this one, is 1 over 1 minus x. Yeah, you already know this. That's the geometric formula. That's just x to the n. okay? Now, we're going to add a little bit to these later on because not only do you have to know the series, you got to know where it converges. Like there's some, does it make sense that this, what's our rule for this one? This is only true when x is where? Between -1 and 1, right? So some of them have like bounds where it doesn't converge outside of that, okay? And we need to use all those tests we just went over and a test on to figure that out. So it's a basic idea. Let's take a look at cosine real quick. When you plug 0 into there, so we're writing the terms out for this one, cosine, you get 1. Okay? The fact that it's a constant and it's just 1 means that cosine of 0 is 1. That's why that's happening. Cool? But if you plug in 1, the next term you get is x squared over 2 factorial. The fact that we do not see an x term, there is an x term there, we're not seeing it because why? What's the only way to make a term go away? The only difference between the terms are the derivatives. So there should be a term that's f prime of 0 over 1 factorial x to the first. That term should be there. What's the only way that cannot be there? If this is 0. And the derivative of cosine is negative sign, and at 0, that's 0. That's why there's no term there. Okay? When you plug in a 3, you get x to the 6th. I'm sorry, when you plug in a 2, yeah, crap, x to the 4th over 4 factorial. Does that make sense? So there's a discrepancy with some of these between what I plugged in for n, like what term I'm on, versus what degree I'm on. The degree is what tells you what term you're really on. Okay? Writing this out like this is a shorthand for it because every other term is 0. But when you plug a 2 into there, you're not getting the second term of the Taylor series. You're really getting the 4th because you're on x to the 4th. You're getting the 4th derivative term, basically. Does that make sense? This term right here, even though we did not build it like this, the 4th degree term has to be the 4th derivative at 0 divided by 4 factorial x to the 4th. It has to be. Okay? It doesn't matter that I plugged in 2 to get that. Okay? Okay. And that's going to happen with something like sine 2. Sine is all the odd powers. Okay? Because all the even derivatives are 0. So let's take a look at an AP question. That'll be fun. We're all about fun. Taylor series. Let's just grab. We went for the one from last year. Do I have the one from last year? Talking to myself. 2017. Good enough. Let's copy this bad boy. Let's just run through. There we go. What's happening here? So, although you are going to memorize your Taylor series, those 5, what they usually do in the BC questions is they make up or don't tell you what function it is, but they tell you like the general pattern. So you'll see here, they're telling you the y value at 0 is 0, the first derivative is 1, and to get any future derivatives, you can use this rule. Okay? And then they're going to ask you, A, show the first 4 non-zero. Non-zero means like you might have to go out like further past the 4th derivative if you have some 0 ones. You need 4 terms, okay? But show the first 4 non-zero derivatives. I mean, terms are right there. Okay? Well, we know that the piece of 4 for this has to start off with what? What did all our Taylor series start off with? What's the very first thing? It's a definition of our Taylor series. The function value. Remember, we built the ln x plus 1 one right here, but that started off with x because the function was 0 there, right? What does my function equal at its center? 0. Kaboom. Plus. The next term is, it's always the derivative divided by the factorial times x minus center to the same power. So we're on the first derivative. What's f prime of 0? 1 divided by 1 factorial times x minus 0 to the first. Okay? Plus, now we need the second derivative. But look what they do. They make it weird. Like, you're not even driving a function. They're telling you this weird pattern. If I need the second derivative at 0, what's n going to be in this rule? N is going to be 1. I need that to be a 2. I need n plus 1 to be a 2. Does that make sense? What this basically says is to find the next derivative, take the last derivative you found and multiply it by negative n. N being the one before it. Okay? So again, I need the second derivative right now, but that means I need to make n 1. That means that negative n is negative 1, and f prime of 0 was 1. So the second derivative at 0 is negative 1. We're going to divide that by 2 factorial and drop an x squared in there. Make sense? The third derivative, I would have to make n 2. So that's going to be negative 2 times the last derivative, which is negative 1. So the third derivative is 2. Cool. And the x is going to be negative. Now the fourth derivative at 0, n has to be 3. So that's negative 3 times the last derivative, which was 2, which is negative 6. Okay. Now what's weird about this is, what's that reduced down to? Yeah, x over 3, right? What function is this? We just did this. This is ln of x plus 1. Yeah, it's the same terms. Cool. They're not telling you that, and they made up a weird way to find it. All right. But it creates those factorials because it's negative n times the last thing. But either way. Cool. So that's that. Now, here's something I like to do. Determine whether it converges absolutely, conditionally, or diverges at 1. That means if you drop a 1 in there for x, what's it going to do? Oh, it also said find the general term. We didn't do that, right? The general term of this is, normally I write like this, dot, 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 is what? And any n term we're on is going to be, where you said this, x to the n over that, right? However, you got to worry about, cool. So when they say show that it converges, what we're really testing at 1, our series is really this, right, with an x to the n there. But if they say show that it converges when x is 1, then I'm just going to put a 1 there. And all that does is turn it into a series that we've seen before. Like this is like the test we just took. Okay, so this is how they make you use those rules. So like show that it converges for this value, or what I'll show you, like, or they'll say find all the values where it does converge. Okay, that's called the interval of convergence. We'll get to that. Do you guys know what this is going to do? Is that series there going to converge? One at the end just goes away. What's that going to do? We're going to show it's convergent by what rule? Alternating series test. The terms are definitely going to 0 and getting smaller. But if you take it away, that's a p series, which diverges by p series test. So the series here converges conditionally. Make sense? Okay. And then they're going to make you like integrate and all that crap. And then, what's this down here? What are they asking us to show? That's the error bound. They want to show the error bound for the 4th degree at a half. So does it make sense that when there's x's in here, like right here, there is no error bound for that? An error bound can only be if like it's just a number, right? If you get an answer. With x in there, there's no error bound for that. So they'll say p sub 4 of a half, which means they want you to plug a half in. Cool. And show that the error is less than this, and we'll get into that later on. Cool. So for tonight, memorize those series. Do those questions I told you, which is page 630. I wrote it. Did I write it down somewhere? Okay. That's your homework to know. Cool.